So now we're going to revisit a few things about kinetic theory. So just remember that kinetic theory, that as temperature goes up, the average kinetic energy of particles also increases. So these are directly proportional. Also remember that basically the gases are made of a huge number of particles in random motion. So they're colliding with each other and they're colliding with other things. So let's talk about the speed of particles, knowing that temperature relates to average kinetic energy. So if we have, you guys should know from physics that kinetic energy equals 1/2 mass times velocity squared. This also becomes this equation. So the energy, the kinetic energy of those particles equals 1/2 mass, and we use this speed equation thing squared. So this is still kinetic energy, and this is speed. So if mass were to go up, speed would have to go down if kinetic energy stayed the same. So let's say you have oxygen and hydrogen, and they're both at the same room temperature. So that means the kinetic energy of oxygen would have to equal the kinetic energy of hydrogen. Those two, even though they're different sizes, would have to be equal. And so because oxygen is a bigger molecule than hydrogen, the average speed of oxygen is going to be slower than the average speed of hydrogen. We can also derive a different equation where if we take the pieces of this and we try to solve for speed, we would end up with the equation U should equal oh, sorry, I'm getting off track. So how does this apply for some other things? So there's effusion and diffusion. So if we think of effusion is when a particle, so if we were to have this container, and let's say we used a vacuum, so this was completely empty, and we poked a little hole in this space. Effusion is the rate at which particles would escape through that hole. So they would escape into that empty space. We saw earlier that small particles go faster. And so Graham's law of effusion basically is this, that the rate of effusion of one gas over the rate of effusion of a second gas is equal to...
This is an all call for Jacob Lee. If you are in the building, would you please report to the main office right away? Jacob Lee. If anyone anyone knows about Jacob's whereabouts, if you would also report to the office, we could use your help. Thank you.
Okay. So anyhow, with these two, this is the these big M's represent molar mass. So notice how they flipped 1 over 2, 2 over 1. So this is inversely proportional. So same as before, smaller particles should get through much more quickly than larger particles. Diffusion, very similar to effusion, except it's just talking about if you put a gas into an empty space. So let's say we have a room. You experience diffusion like if somebody walks into a room who's wearing a really strong perfume, and those perfume particles travel throughout the room until eventually it hits your nose over here, and then you smell it. So this is why sometimes in hospitals you'll see that you're not allowed to wear certain scents, because if you smell it, what is actually happening is that your nose, the receptors in your nose are actually making contact with actual particles of that substance. Again, we know because of the kinetic energy that's small and being related to mass and velocity, that smaller particles move faster. Also, another consideration, though, is that we know that particles will bump into each other. So, for instance, if I have, and they have random movement. So, for instance, this particle might go there, and that particle might go there, and this particle might be going that way, but it's going to bump into another particle. So, we have to consider something called mean free path. So, mean is a term for just a straightforward average. Free path means how far can a particle go before it hits something else. So in this case, like this arrow that I just drew would be the free path of that particle. And maybe this arrow would be the path for another molecule. So if we took all of those paths and added them up and found the average, that would be the mean free path. So obviously the more condensed something is, the smaller that mean free path is going to be. In fact, I think, so generally if something is at a high pressure, it's going to have a smaller free path.